Hello everyone and welcome to this Introduction to Machine Learning tutorial. In this video, we will go through a multiple linear regression example for beginners. Now, please note that this video is actually video part 3. And if you haven't watched part 1 and part 2 already, I'm going to have links in the description, which I highly recommend you do that first. In part 1 video, I have explained what is machine learning, and I also went through the machine learning process. So all the steps you have to take when you're running machine learning and all the tasks you have to take within each step. Additionally, I went through the problem formulation phase, which is actually the step 1 of the machine learning process. Also, I have explained which libraries we will be using for this tutorial and from where to download the raw data and the notebook that I'm using for this tutorial. In part 2 video, we went through the data preprocessing phase and how to split our raw data. So here is where we've done our EDA analysis, so exploratory data analysis, investigated the distribution of the data, we've done data cleaning, we've done feature selection, and we've also splitted our data using holdout validation. In this video, we will go through what is linear regression analysis and how it works. Then we will run a linear regression model using the data we have prepared in video 1 and video 2. Then we will evaluate our model, and at the end we will discuss how we can use our linear regression model in real life scenarios. Right, so what is linear regression? Linear regression is a very famous machine learning model that is used to predict numbers and not classes. So we are not predicting if it's a dog or a cat, we're actually predicting a number. The way it works now is that it models the relationship of two plus variables by feeding a linear line or equation to observe data. So here we have two variables, our x and our y, and then the values. And the way regression works is that we feed a line of best fit through the variables. And I'm not going to explain how it works now, I'm going to explain later on. In linear regression now, you have one dependent variable, which is your y, what you are trying to predict, and one plus independent variables, which is going to be your x's. In this case, we only show one, but in our case, what we've shown in the previous videos is that we have 12 features, 12 independent variables that we are going to use to predict our y, which is going to be the revenue. The fourth point I have is that before we attempt to model the data, we should check if there is a relationship between the variables first. And a good way of doing this is to use scatter plots to visualize the data. Now, the reason I said this is because of these four famous plots down here, which they are called Anscombe's quartet. So these plots now, they have identical descriptive statistics, which means they have identical means, standard deviations, variances, correlations, and regression lines. What I'm trying to say here is that if you run a correlation or a regression before you visualize your data and investigate if there is a relationship, you're going to get high numbers for all four graphs, which means that there is a relationship. But would you say that there is a relationship in all four graphs? I would say no, personally. Looking at the first graph, we can see that yes, there is a relationship between x and y. So as x increases, y increases too. So a linear regression here, it makes sense. Looking at the second graph now, we can see that yes, there was a relationship, but up to a point. Then we have diminishing return. So a linear regression doesn't make much sense here. We probably have to use a polynomial regression. Looking at the third graph now, we can see that yes, there is a relationship between x and y, but we do have one outlier there which skews our data and it drags the regression line further up. So in this case, we should visualize and investigate our data and remove that outlier, so the linear regression is going to have a better performance. And looking at the fourth graph here, we can see there is no relationship at all. It should be a vertical line like this, but just because of this outlier or this data point right here, it drags the regression line from a vertical line to be a linear regression line similar to the other graphs, and it indicates that there is a relationship between x and y, which in the real case, when you do visualize the data, you can see that there is no relationship. So the idea is that it's best practice to always visualize your data before you try to model it. Right, moving on, another measurement of relationship between two variables is the correlation coefficient, which we have explained in the previous video how to run it and how to interpret it. So you should go and watch that video. However, my next point says that even if it seems to be a relationship between two variables, so you get high correlation coefficient or high regression, it does not imply that there is actually a relationship. So correlation is not causation. So the best way to understand this point is that let's assume that on this graph, our X was the temperature in the UK and our Y was the sales of a store in the US. And we could clearly see that there is a relationship. However, we both know that the temperature in the UK cannot really affect the sales of a store in the US. So correlation is not causation. It doesn't mean that the temperature is what caused the sales to go up, which is the point of my second point. Right, back to linear regression now. The mathematical equation of a linear regression is y equals a plus b times x. X is our independent variable, Y is our dependent variable, what we are trying to predict, B is the slope of the line, which is the weights or the coefficients, and then A is the intercept, which is basically the value of Y when X equals 0. Now, I'm just going to read these 3 bullet points here and then try to explain them visually how they work. The most common cost function used in linear regression is the least square error function, which is the sum of square errors over the training set. So we're basically trying to minimize the least square error, which is how far off the predictions are from the actual values. To calculate now the least square errors, firstly you have to calculate the difference of the actuals versus the predicted values, which this is called the residuals. In order to find the least square error now, you will have to find the optimal parameter values, which is our B here, so the weights or the coefficients, that minimize the sum of square errors, which is basically the sum of square residuals. Right, so the way it graphically works, which is easier to understand, is that it starts by feeding a straight line, which is our iteration 1, as you can see it. And the next step is to calculate the residuals, which is the difference between the actuals and the predicted value, which is going to be our line. So it does this basically. It calculates the difference from the first iteration to the actuals. So this is iteration 1, which is actually going to be our prediction, iteration 2, data point 2, data point 3, data point 4, data point 5, data point 6. So now we have all of our residuals, which is basically the difference between the actual data point with the predicted data point. And then the formula it sums all those residuals together, all the red lines together, and then it squares them. And the sum of square error is basically the cost function that we're trying to minimize. So this is the first iteration. It does the same with the second iteration, and it checks if the sum of square error is less. If it's less, it continues to drop from that direction until you find the line of best fit, which is called until you converge. And then you don't basically improve your sum of square errors. If you keep moving downwards, it actually increases. So it's going to stay over here. So this optimization technique that I have just explained is called gradient descent, which is this graph over here. So what I'm going to do is that I'm going to read the bullet points first, and then I'm going to explain you how it works. So the optimization technique used in linear regression is gradient descent, which attempts to find the local or global minimum of a cost function. So in a linear regression, the cost function that we usually use is the sum of least square errors. Different models have different cost functions, but they do follow a similar optimization technique, which is gradient descent. Gradient descent finds the direction or gradient that the model, or the line in our case, should take so that the errors will be minimized. So for example, it started in iteration 1 and then it moved the gradient, the weights on the right side. If the sum of square error was increasing, then it was going to try on the other side, so readjusting the weights. Direction refers to the weights A and B and how those weights should be tweaked to further reduce the errors. So A and B is basically our A and B from our regression line. So how should we tweak those weights or coefficients so that we can find the line of best fit by minimizing the error? And then the model will iterate until converged. No further improvements can be done. So until you find the local or global minimum, it's going to keep iterating. As soon as it finds that global or local minimum, then it's going to stop, and we call it that it's going to be converged. Right. So the way it works is that we start from iteration 1. We check the sum of least square errors. Then we check iteration 2. So we've seen that we've adjusted the weight this way, and the error has reduced the loss. So we keep adjusting them. So we adjust them again, and then we can see the error has dropped. We adjust them again, we see the error has dropped. We adjust them again, we see the error has dropped, which is iteration 5. We adjust them again, and we see that the error has increased in this case. So iteration 6. So this graph does not really correspond to this graph. It's randomly, because I've randomly created this. The reason I've done it this way is so that I can show you that this is actually the local minimum. So the local minimum I set here, and there is actually a global minimum that I have to play with the gradient descent and how I calculate this so I can find the global minimum. However, because this does not correspond to this, don't think that iteration 10 is actually iteration 10 from here. I've just done it so I can explain local minimum and global minimum. Right, so I hope you have a very good understanding now of what is linear regression, the things you need to be aware, and how it's been calculated. By the way, if you feel that you're getting enough value out of this video, I would really appreciate it if you click that like button and subscribe to my channel, and also enable notifications, please. Right, the next step now is to actually run our linear regression model. To do this now, we're going to visit SKLearn, which is the library we are using for this tutorial, and see how we can run a linear regression model. So I'm just going to scroll down to the examples, and all I'm going to do, where are the examples? I'm just going to copy and paste the linear regression model from here. By the way, if you've noticed in video part 1, I've explained that I am using SKLearn and I'm importing linear regression from SKLearn. So if you haven't done that, you need to run this. I'm just going to copy the linear regression here, copy it, paste it here. I'm going to say LM equals, so linear model equals linear regression. Additionally, I'm also going to fit the intercept because I do want to make some predictions afterwards. So I'm just going to copy this, paste it here, and say fit intercept equals true, and then run this. So you can see it didn't return anything. All it did is that it initialized a linear regression model. Note that we haven't had to do any of the calculations we've mentioned above. All this is done by SKLearn. So this is why is that all these libraries and the whole open source thing is amazing. The next thing I have to do is to actually fit my raw data into the linear model I have just initialized. To do this, I can go back and see how the fit works. So the way it works is that I have to first call in my model that I have just initialized, then say fit. And what do I want to fit is that I want to fit my training data, which is what I've done in step 6. So the X train and the Y train. So I'm just going to copy this, paste it, and then say Y train down here, and then just run this. And we can see it didn't return anything. It worked fine. Right, the next thing we have to do now is to evaluate our model just to see how well it performed. So if we quickly go back to the machine learning process, you can see that we are on step 6 now, where we are evaluating how well our model did. So one of the most famous evaluation metrics for a linear regression is the R-square. And there is 2 ways of calculating R-square. The first one is through the official documentation of linear regression model. If we scroll down, we can see that we have a method here, a function called score, where it takes the X and the Y and it returns the coefficient of determination, which is the R-square. To do this, I'm just going to quickly run it. So I'm going to say lm.score, open brackets, and in brackets, I need to fit the x and the y. So please note that this score now is actually on our training data set. It's not on unseen data. And it returns 79%. So I'm going to quickly run all the R-squares and then explain what is R-square and how to interpret it. I'm going to say print here, and I'm going to say the accuracy on the training data set is, and then close brackets, put comma, and paste this. Let's see. There we go. The accuracy on the training data set is. Additionally, another way of running R-square is through the R-square function from SKLearn, and this one takes the y true and the y predicted. So I'm just going to call it quickly. I'm going to say R-square just to test it. I need to say lm.r-square. And remember, now we need to put the y true, so the y train, and then we need the y predicted. However, we don't have the y predicted. We haven't calculated yet. So in order to calculate the y predicted, I'm just going to show you how to do it. I'm going to say y pred equals, so y predicted equals, and the way to do this, I go back to my SKLearn linear regression model. I scroll down and see here that there is a function called predict. So I'm just going to say, how did I name it? lm.predict. So I'm going to say lm dot and then predict, open brackets, and I do want to predict my x train, because if you see what it takes the, where is it? Sorry, it takes the x. So I put it in and then run it. So now I have my predicted values. Just to quickly visualize what this is, y train now is these values over here that we see, which is length 143, and then y predict now is again, it's going to be a length of 100. Let me do the shape so you can see it's exactly the same. Sorry, remove that. So you can see the shape is 143. Again, is 143 values. However, these values now are the predicted values, and the y train are the actual values. Right, going back here now, I need to say, I need to put this y predict, copy it. I'm just going to remove this quickly and put it into my R-square function over here. And then if I run this now, we get an error that the object has no attribute R-square. Maybe I don't need the lm. Let's see. Yeah, I don't need the lm. And additionally, I do want to add the print, so you can see what's going on. Print the accuracy on the training data set, the is, and I'm going to say the accuracy number 2, because this is calculated on a different way. However, it's still exactly the same number. So if we compare them now, we can see that both numbers are exactly the same. However, I'm using two different ways of calculating them. This is because not all classifiers do have a within score function. So we do have a separate R-square function provided by sklearn. The next thing we're going to do is to calculate the model accuracy on the testing dataset. So you remember how we split our datasets into training and testing. Now we want to evaluate this model, how well it does on unseen data. And the way to do this, I'm just going to copy the first one using the score function, but they both give you the same numbers essentially. And I'm going to say the accuracy on the testing dataset is, and I need to change this x train and y train to x test and y test, which is, remember here, step 6, where we split the data into x train and x test, training and testing basically. So I'm going to put this x test, and this is going to be the y test. And then if I run it, we can see, I also want to leave an empty space here. So some, there we go. So we can see that the accuracy on the testing data set is 0.75. So we can see that it dropped from 0.79 to 0.75. This is usually, if not always, the way that the machine learning model works. Your accuracy is always going to be higher on the training data set because it's data that the model actually sees versus the testing data set, which is all new to the algorithm. So you should always evaluate how good is your model on unseen data. Now, some notes about R-square. The accuracy score, which is this score over here, represents the coefficient of determination, which is actually the R-squared. They are the same thing. This is at max 1, however, it can be negative. It will be 0 if you predict the mean of y for all your observations. Additionally, R-squared is a measure of how close the data are to the fitted regression line. So what this means is that the closest the regression line is going to be to your points, the higher the R-squared is going to be. So we always aim to have a large R-squared. And the last point I have is that in this case, we can say that our model explains 81% of our training data. Actually, I need to change this because remember, we are running random split. So every time I run it, it uses a different training data set and a different testing data set. In this case, we have 79%. We can say 79% on explain 79% of the training data and 75% on testing data. And this is how you would interpret your coefficient of determination. Another key important metric that you should always keep track on when you're running linear regression is the root mean square error. So firstly, I'm going to try and run it and then explain what it is and how we can interpret it. So to run it, I'm going to use a predefined function by SKLearn, which is the mean square error, which I have the link over here. So if we visit the link, we can copy the function and we can also see what parameters it takes. So this one takes y true and y predicted. So if I go back, I just call it, and in the brackets, I need to put the y true and the y predicted, which is the same as this one above here. So copy it, paste it, run it, it works fine. And then we basically need to take this number and take the square root of it. To take the square root of it, I'm using math library and the function square root. So I can just copy this, come down here, paste it at the beginning, and then run it, and then we can see the root mean square error. Additionally, I just want to print it because we're going to print more metrics. So I can say the root mean square error on the testing. I'm going to put the training data set here is, and then run this as it is so we can see straight away. I also want to leave an empty space, and I also want to print the root mean square error on the testing data set too. So I'm seeing data. So I can copy this, paste it, change training with testing, and here I need the y test. And I also need the y predict, but for the test this time, because our y predict is actually for the training. So I can copy this, the whole function, paste it in here, and instead of saying lm.predictXtrain, I'm going to put lm.predictXtest, and then run this, and then we do have the root mean square error for the testing data set too. It's actually less here, so this is actually a good story. So the way to interpret this now is that the root mean square error, not Q, is the standard deviation of the residuals. Remember, the residuals is the difference between the actual data points to the regression line. So those red dots there, the red dotted dots. Residuals is the difference between the predicted value and the regression line. Hence, root mean square error is a measure of how spread your residuals are. The next metric that you should keep track when it comes to linear regression is the mean absolute error, which you should look to minimize. So the way to calculate it now, we will use a predefined function from SKLearn, which I have the link down here. So I'm just going to go into SKLearn. I'm just going to copy it, and then I'm just going to paste it. I'm going to go back to see what it takes. It takes into parameters the y true and y predict, which is similar with the root mean square error. So I'm going to open brackets and I'm going to put the y train and the y predict. Copy, paste it, run it, and then we can see the error, the mean absolute error down here. So I'm just going to copy the print too. So we can print it, close it, and we can say the mean absolute error on the training dataset is, and I also want to print it on the testing dataset. I need to leave the space. So it's going to be the mean absolute error, and I'm just going to copy what we have up here because it does take the y test and then the y predict for the test. Sorry, it took me a while there. So this is going to be the y predict, this one. So I copy it, paste it. I need one more bracket. And then if we run this now, we can see the two mean square errors for the training and also the testing dataset. So we have a similar case. We can see that the mean absolute error has dropped on the unseen data, which again is a good story. So the way to interpret this now is that the mean absolute error is the average of all absolute errors. And the absolute error is the difference between the true value and the predicted value. So we calculate the true value, we take the true value minus the predicted value, and we take the mean of all of those errors. And this is, again, the lower this is, the better it is. It means that on average, in each prediction, you're about $1,600 off. The next thing we're going to print is the coefficients, which are basically the weights that we will use to make our predictions. And the way to call them is just by saying linear model dot, and then going into the official documentation of SKLearn, we can see the attribute here, coef underscore, which are the estimated coefficients. So if I copy it and paste it and then run it, I get my coefficients. So remember, each one of these numbers corresponds to our X variables, our independent variables. So if you remember, we have 12 independent variables, so we should have 12 numbers here. And if we do count them, it's 1, 2, 3, 4, 5, plus 5, plus 2 is 12 coefficients. And now I just want to print them, so I'm just going to say print. Then into brackets, I'm going to put coefficients. Sorry, this one, space, comma, close it, and then I'll leave the space too. And then run it again. There we go. And the last thing we want to print is the intercept, which is the expected mean value of y when all of our independent variable x's equal 0. And we will use this intercept later on to make predictions. Same thing with the weights. However, the intercept is only going to be one number. It's the expected mean value of y when all x's equal 0. And to call it now, we can go into the official documentation, into the attributes, and see how we call it. It's intercept underscore. So I copy it, I paste it. I do need the linear model at the beginning, and then I run it, and I can see the mean value over here. Additionally, I do want to print it, so I'm just going to say print intercept, comma, close brackets, leave some empty space. And there we go, we have our intercept value. Right, the next thing we're going to do is to plot our actuals versus predicted values, so we will be able to visualize how well our predictions are. And to do this, I'm going to start by setting the plot figure. So I'm going to say plt.figure, I'm going to open brackets, is fig size equals, and I'm going to say 15,10. And if I run this, it's fine. So we have our figure. Then I need to plot the x and the predicted, the y and the predicted y. So I can say plt.scatter, and I need my y train, comma, my y predict. And I want the color to be green. So I can say color equals green. And if I run this, we can see this is the actuals and this is the predicted. Additionally, I do want to fit a straight line, not the regression line. I just want a perfect line here, so it's easier for me to interpret the results. So I can say plt.plot, and I can use the y-train mean and max to do this. So I'm going to say y-train.mean. I can say y-train.max. And then I can paste exactly the same thing, copy, paste this. I want the style of it to be dotted line, not lines with the dots. I also want the color to be red, and I want the line width to be 3. So if I run this, there we go. Additionally, I do want to add the labels, so the x and the y. So I can say plt.x label, and this is going to be the actuals. And then I can say plt.y label, and this is going to be the predicted. And I want the plt.title, which is going to be the actuals versus predicted values. There we go. Let me make this capital. Right, the way to interpret this plot now is that this red line, which is not the regression line, is where we assume that we got all of our predicted values 100% correct. So where we say where the actual is 500, the predicted value is 5,000. The predicted value is exactly 5,000. Where the actuals is 10,000, the predicted value is exactly 10,000. So the closer the data points are to the red line, the better the model is, and vice versa. The further away the data points are from the line, the worse our prediction is. So for example, this data point over here, we can see that it has actuals 5,000. However, we predicted 4,000, which is not that bad. It's quite close to the line, so it's good. However, this data point over here, or this one, or this one, or this one, let's start with this one. The actual value of this one is about, let's say, 6,000. However, we predicted more than 15,000. And the same case goes with this data point. So we have to do something for those data points, as our predictions are not that great for those two data points. However, before we discuss what we can do for these data points here, I do want to plot the residuals first. To plot the residuals now, I'm going to use SNS resiplot, and I'm just going to copy the code I have up here and readjust it so we save some time. So this is going to be the figure, then I'm going to replace the scatter to be the SNS.residuals plot. Remember, the residuals is the difference between the Y actuals and the Y predicted. That's why I leave Y train and Y predicted over here. Also, I need to change the color to be green. I don't need this straight line, the red straight line. Our X label now is going to be the actuals. So it's actually going to be the actual revenue, because remember, our Y is actually the revenue. The Y label is going to be the residuals. So I'm just going to copy it, paste it over here. And then the title is going to be the actual versus the residuals. Is it actual? Yeah, actual versus residuals. Okay, there we go. Right, the way to interpret this now is that the zero dotted black line is where we got our predictions 100% correct. So basically this data point here was bang on, which is around, I don't know, $1,000. We actually predicted it to be almost $1,000. And then the furthest away the data points are to this line is how much far off our prediction was. So for example, for this data point here, we can see from 0 all the way to, I don't know, maybe 5,000. We got this prediction wrong by $5,000, which is actually a lot. So what we want to see here is how sparse our residuals are, just to see how much off our predictions are, and where is the concentration of the data points, which I would say is between minus 2,000 to 2,000. Maybe we do have some points in the 4,000s, but I would say the majority is between minus 2,000 and 2,000, which is actually what this number here says to us. So the mean absolute error and also the root mean square error is between almost 2,000, and this one is almost 2,600. Right, so the action here will be to go back to our raw data and see if we can remove those outliers and then rerun our model and see if we can improve our predictions. However, I would say that the residuals, they look quite okay to me, up and down. Is only these few data points over here at the top, which is, if you have time, then you can go on and see if you can improve your model. So what we are discussing here is basically, if we go back to the machine learning process, is the parameter tuning step, which is where we adjust our parameters or hyperparameters to try and improve our model. Now, linear regression does not have any hyperparameters as far as I'm aware of. So the only things we can do is to see if we can remove outliers, or to add or remove new features, or create calculated fields and then fit them again in the raw data, and then train our model again, run it and evaluate it and see if we can improve the model. However, for this tutorial, because it's quite lengthy as it is, we are not going to do that. We're just going to continue into making predictions with the current model we have. Right, moving on to the next step now, which is how we can use our linear regression model to make predictions. And by the way, if you feel like you're getting enough value out of this video, I would really appreciate it if you click that like button and subscribe to my channel. Right, the first thing we have to do is to create our coefficients data frame. And to do this, I'm going to pass coefficients into an object first and then into a data frame. So I'm going to say lm.coef and then underscore, if you remember. And then if we print this, we can see our coefficients, which is what we've shown in the step above. There we go. So I want to pass this into a data frame now with column names, so I know which coefficient corresponds to which feature. Right, then I do want to reshape this, because if I check the shape of it now, it's actually 12 rows, and I do want to make it 12 columns. So I can say coef equals coef dot reshape before I pass it into a data frame, -1 to 12. There we go. And then I want to create my data frame, which is going to be coef underscore df equals pd.dataFrame open brackets. Here I need to put the object I want to pass into a data frame, and then I also need the columns, and the columns is going to be the column names now. And to get the column names, I need the column names of all of our X features. So if I scroll back here where we split it our X and Y, I can get X dot columns from here, but it's not going to work because I've used values. So what I can do is that I can replicate this X, and I can say X2 equals the same thing, but I'm going to remove the values now. So now I have a new object, X2, which if I print it, I'm going to print it down here so you know what's going on. Create new, and then I print it. Is all of our X features and all the data, but all I need is the columns. So I can say dot columns. So I have all the columns now in the order I have used them before. So if I copy this and paste it into the columns, and then I display my new df, you can see now that I have created a data frame that has all of our features. So you can see these 12 features, and then the value of their coefficient, their weight, which is what we're going to use to make predictions. Right, the next thing we have to do now is to declare our variables, and this is going to be the variables or the features we have used to train the model. So it's going to be day equals, I'm going to leave it empty for now. Then we have visitors, I'm going to leave it empty for now. Visitors, then we have the marketing spend, so I'm just going to copy it, paste it, equals, and then we also have the promotion. So I'm just going to say promo equals and leave it empty. Right, the first step I'm going to do is that I'm going to first create the prediction formula and then fill in those variables and run the formula to see how it predicts or how it works. So to create the formula, prediction1 equals, I'm going to follow the regression formula for prediction, which is y equals a plus b times x plus, and then all the other variables we have over here. So the first thing we need is the a, which is the intercept. So the intercept is what we posted up here. So I'm just going to copy this. Then I'm going to paste it down here into brackets. Then I need to say plus. And the next variable I'm going to use is the day. So to use the day, I'm going to pick the coefficient from this data frame we've created here. So I'm going to say coef df. And then into brackets, I'm going to put the day, which is going to be the variable over here. And then this is going to be into brackets. Actually, I need the dot values, and I need the first value. So I can select only the number. And this has to be times 1, because if you remember, this is a categorical variable and we only use zeros and ones. So it's only going to be one day. So we're only going to use one of the numbers over here of the day. That's why we have zeros and ones. Then the next thing is going to be the visitors. So again, I'm going to use the coefficients table we've created up here to get the coefficient for visitors, which is this number over here. And I'm going to put visitors into brackets over here. There we go. And this is going to be times the number that I'm going to put here in the variable. So visitors. And then I'm going to leave this into brackets. And then I'm going to move on to do the same thing for marketing spend. So I can say plus. I'm just going to copy the whole thing, paste it. Actually, again, I need dot values and take the first value. I need the same for marketing spend. So I'm going to replace visitors with marketing spend and then say dot values and then take the first value. Let me just press enter here so we know what's going on. And then we also need the last thing, which is the promo. So I'm going to copy, because promo is a categorical value, the same way as state, I only need the zeros or ones. So I'm going to take the coefficient promo from here, coef.df promo from here, the first value, which is going to be, depending what we're going to put in here, times 1, which is 0 or 1. Right. And then I can print the df, so I can say print the predicted revenue is, and then leave space, close this, oops, let's say comma. What did I do here? This one has to be this one, and then print the prediction 1. Right. Before I run this now, I want to fill in some random features over here, some random variables. So I'm going to say that the day equals day name Friday. So I'm just going to copy the name to be Friday. The number of visitors, I'm just going to put randomly there a number, totally random. The marketing spend, again, I'm just going to put a totally random number there. And then the promotion, I'm going to say it's going to be promotion red. So I can copy promotion red and put promotion red over here. So if I run this now, we get an error. The error is marketing spend, and it's because I need an underscore over here. And I also need to replace the visitors over here. I've noticed when I copied and pasted the formula from visitors, I need to replace these visitors with marketing spend. Otherwise, it's going to use the wrong number variable from over here. Right. If I run this now, again, I get an error, which is, oh, come on, what's the error now? Oh, now it works. If I press enter, it doesn't work. So I don't understand. It wants everything in one line. Anyway, the predicted value of the predicted revenue now is $27,833. So what this tool does now is that we can use this tool to say, oh, I know next Friday we're going to have about this number of visitors. I don't know. I'm going to change it again. We're going to have about 8,000 visitors. We are planning to spend about 5,000 marketing spend, and we are planning to run promotion red. So how much are we going to generate? And if I run this, we can see that we should estimate to generate about $31,625. Right, so now you know what is regression analysis, how it works, how to run it, and how to use it to make predictions. And in the next step now, we're going to discuss how we can apply this model in a real-life business scenarios. And I have made some points down here. So the first point I have is that we can use this model to create a prediction tool for upcoming marketing campaigns. And the way to do this is that we can deploy this model with the current coefficients we have into either Excel, Power BI, Tableau, or any other CRM system, and then pass it down to the business or the marketers so they can use it to fill in the numbers and plan ahead for the future. The next point I have is that we can analyze past marketing campaigns and suggest what has worked, what did not work, how much money we could have made, and what we should change in the future. So this is called campaign optimization, which is actually very, very famous in marketing analytics or digital analytics. So what I mean here is that you remember how we have identified in our exploratory data analysis which promotion performs the best. We can actually use this in mathematical terms using the regression formula and say to them, look, next time try to only use promotion, which one was the most successful one? The promotion blue, because it's what's generating most of the money based on how much marketing spend you put in. The next point I have is that we can predict the potential of either stores, account, channels, or campaigns, and then compare their potential with what they actually achieve. Then we can create an index, so overachieving and underachieving accounts, channels, campaigns, or stores, and we can grade them. So grade A, grade B, grade C, and grade D. And then we can use these grades to go back to the business, so we can help push grade B, D, C accounts into being more of A accounts. Again, this is a very famous and very widely used project in the analytical data world. And the last point I have, which is more of an AI point, artificial intelligence point, is that we can deploy the model in a server or in the cloud and automatically readjust the campaigns that generate the most of the money depending on the day. And at the same time, we keep running different A and B new campaigns and new ideas, so we can readjust them once we do find a better performing versus the existing ones. Right, so this is it for this lengthy introduction to machine learning linear regression example for beginners tutorial. I hope you enjoyed this video and you've gained enough value out of this video. And if you feel like you did, I would really appreciate it if you click that like button and subscribe to my channel. Additionally, if you have any questions or there is something I didn't explain very well, please let me know in the comments below. In the next video, I'm going to be doing a similar tutorial, but this time I'm going to be using a classifier, not a regressor. So I think I'm going to do logistic regression. So please enable notifications so you're going to see when that video is going to be uploaded. Thank you very much for watching and see you on the next tutorial.